Einstein's theory of special relativity starts with two basic postulates. These are what we take for granted, and then we look at the implications of these postulates, and that's what gives us special relativity. This is a little bit like the way we did the kinematic equations at the very start of Physics 1. Our initial assumption was that acceleration was constant and motion was in one dimension. After we assume those two things, we work out the kinematic equations. Now, those equations themselves don't prove acceleration is constant or motion is in one dimension, and these two postulates that we're going to use don't prove special relativity is right or wrong. Having said that, however, there are many, many experiments that have shown that the two postulates and relativity match up with reality as well as we can measure. The first postulate is very simple and something Galileo would have been able to believe, and it is the laws of physics are the same for all inertial observers. Inertial just means not accelerating. If you think back to all the physics labs you did in the first semester, none of them would have been any different if you had been in the back of a large cargo plane as long as it was flying at a constant velocity. The fact that you were moving relative to the surface of the Earth wouldn't have changed them. There's no natural difference between moving 200 meters per second and being at rest, and one of the big ideas of relativity is there really is no such thing as at rest. All velocities can only be interpreted as relative to some other body. Now, for us, usually what we care about is the other body being the Earth. That's how we define motion as being significant outside of physics. But there's nothing physically special about the Earth, and if you're flying an airplane, your speed relative to the air is more important to you than your speed relative to the Earth. The second postulate is the crazy part, even if it doesn't seem like it at first. It says the speed of light in a vacuum is the same for all inertial observers. It doesn't sound bad, but here's one of the consequences. You remember last semester when we talked about vector addition, we said, let's say you and your friend are on a railroad flat car riding through the country at 20 meters per second. You have a baseball and can throw it at 15 meters per second. If you throw it towards the front of the train, you and your friend both say it's moving 15 meters per second. Someone on the ground, though, as the train goes by, would say the speed is 20 plus 15 or 35 meters per second. This is just the vector addition we started Physics 1 with. Now, instead of a baseball, imagine you have a flashlight. The train is still going 20, and you shine the flashlight towards the front of the train. You and your friend again say the light is moving at the speed of light in a vacuum, 299,792,458 meters per second. The person on the ground watching the train go by, Newton would expect them to add 20 meters per second to that to get the speed for the speed of light is 299,792,478. They don't. When they measure this, they get the exact same thing you do. This is our first conflict. Newton and Einstein can't both be right here. And one thing we know is if Newton was very wrong, if, for example, the 15 and the 20 together equaled 20, someone would have figured it out long ago, probably Newton himself. The change has to be very, very small. When we learn the math, we're going to see that the baseball problem is what changes, and instead of 35 meters per second, we get this 34-point long string of nines meters per second. It's about 1/10 trillionth of a meter per second difference. So we can't really blame Newton for missing out on this. There are other consequences of this. One of them is what's called the relativity of simultaneity. If we say you're on a train car and everything in relativity is based on trains because that's how people got around in the early 20th century, you're in the middle of the car, there's a light in the ceiling of the car in the middle. When you turn the light on, you see the light hit the front of the car at the same instant it hits the back of the car. Somebody on the train station platform watching the train go by, though, sees something different. They see the light pulse expanding from the center, traveling at c in both directions, front and back, and they see the back end of the train car racing forwards towards the light pulse, and the front end of the train car racing forward away from the light pulse. So we put in some crazy high speeds, so there's a noticeable difference. Let's say the observer on the train platform says the train is moving at 0.9 c relative to him. He then sees the back of the car moving towards the light pulse with an effective velocity of 1.9 c. Because the light's moving towards the back of the car and the back of the car is moving towards the light, we add them. He also sees the light pulse chasing the front of the car, and it has an effective velocity of 0.1 c. because the light is moving at c and the front of the car is moving at 0.9 c. So of course he says the light pulse hits the back end of the train much earlier than it hits the front end. So you can't agree with him on whether it was a simultaneous pair of events or not. One important thing to keep in mind is nothing is really going faster than the speed of light, and we'll never find anything going faster than the speed of light. This effective velocity that I'm talking about here with this 1.9 c, this is kind of like if we had two planes where each is moving at 500 miles an hour relative to the ground and they have a head-on crash. The effective crash speed, the rate at which they close the distance between them, would be 1,000 miles per hour, which is faster than the speed of sound, but we know there won't be a sonic boom. No one was really going faster than the speed of sound. We should also talk about inertial frames and observers and seeing versus observing. You may have seen this already if you've ever seen a pile driver at work from far away, because it's very, very loud and you can see it from a pretty fair distance. It's just a giant hammer that's lifted up and slammed down onto a steel beam. If you're far away, you see it slam down, but it takes a second for the sound to reach you. You can even do this if you have a basketball and you're, at the other end of a street and bouncing it loud. Somebody can tell the difference between when the ball hits and when they hear it. One that most people are familiar with is if you see a lightning flash and you start counting seconds, every 5 seconds is another mile away until you hear the thunder and then you stop counting. The reason that we do this is sound is only about 1/millionth as fast as light. The same thing really happens with light. It doesn't arrive instantaneously any more than sound does. We never notice that because in the first place there's nothing faster to tell us start counting before the light gets there. And in the second case, it's so ridiculously fast on the human scale, we would never sense the delay. Now, we don't want to include the travel time of light in every problem because that's just going to add to our difficulty. The way to get around this is to imagine that instead of being by yourself, you have this lattice of meter sticks and clocks put together kind of like Legos or an erector set or something, so that every meter, let's say, there's a clock in every direction and there's meter sticks connecting all the clocks, and you've got a friend sitting at each clock. What this means is whenever anything happens, however far away it is from you, you will have a friend right on top of it with a clock and a meter stick. And all these clocks are synchronized because they're in one inertial frame. They're all traveling at the same speed you are, which as far as you're concerned is 0. We build this setup so that we can keep track of what are called events. An event is basically what you're talking about if you make an appointment with someone. You've got to give them 3 coordinates in space as far as where to be, and you got to tell them when to be there, and that's your time coordinate. So you put those 4 numbers together, and that's a point in space-time or an event. This means that, let's say you're at the origin of your reference frame, and there's something happening 30,000 kilometers away in the x direction at time t equals 2.55 seconds. At that distance, it would take another 1/10 of a second for the light signal from this to reach your position. We don't want to have to worry about including that, so what we do is we know that you've got this infinite array of friends. There's somebody right there at that point, and they have essentially no delay for travel time since they're right there on top of that event. Now, one of the most famous weird results of relativity, let's design the simplest possible clock we can think of. So we just have a vertical pair of mirrors and a light pulse bouncing back and forth between them. We could make the time for one round trip of light to be 1 second, but that means our top mirror has to be 150,000 kilometers above the bottom mirror. It doesn't really matter though if we could adjust this to a nanosecond and make it a much smaller clock that would fit in your room. In any event, it's a very simple idea. The light just bounces back and forth between these mirrors, and there's something that counts it every time it happens. The time of the tick we could call delta tau, and that's just 2d divided by c, where d is the distance between the mirrors. Now, if you're going past a train station or the Earth or whatever, if this is a spaceship, When someone drives past you with this clock and they look, they see the pulse leave the bottom mirror, hit the top mirror, go back to the bottom mirror. But while you only see it move straight up and down, they see it move in the direction of travel here as well. You see it cover a much shorter distance. It's just going 2D. On the other hand, this is going the hypotenuse of two triangles, and the hypotenuse here is longer than each of the legs. One of the legs is d, and the other one is relative velocity times half the travel time. That means if this person on the platform here is going to measure the same speed for the speed of light, and light is going a greater distance, the only way they can make that work out is if they say it took light a longer time. So while you say it only took a second or a nanosecond or whatever for this light to go up and down and the clock to tick, this person will say, no, it took significantly longer since it's going that longer distance. And what that translates to is they would say your clock is slow. If you want to see what the math looks like, vertical distance is 2d, horizontal distance we would call v delta t. That actually shouldn't be over 2. That's half the distance. So horizontal distance is v delta t. And then the hypotenuse is 2 times the square root of, well, no, there should be a 2 there. The hypotenuse is 2 times the square root of L squared plus D squared. We do a little algebra and we see that what they measure for the length of a tick, a round trip of this light, is what you measure divided by this weird factor, the square root of 1 minus v over c squared. This factor of 1 over 1 minus v over c squared comes up so often that it gets its own symbol, and that's called gamma. This is referred to as the time dilation factor. When we say you see the other clock is slow, this is not at all the way ordinary people use that phrase, that this clock is slow. When they say this clock is slow, what they mean is it's set behind the correct time. This clock that we're talking about is not behind, it's literally slow. If we ever had a clock like this on Earth, we would throw it out because we'd constantly have to reset it. The point of making the clock so simple is that this is an effect on time itself, not some kind of internal stresses on the gears in a watch or something like that. Any way you can measure time, you'll get that it's different on the train than on the platform. We could also say, what if the platform observer has been to the same store you did and they got a similar clock and it's standing beside her? When you go by, you'll see her light pulse taking the triangular route, and you'll say her clock is slower than yours, and it'll be by the exact same factor, because the one thing you could agree on in relativity is relative velocity. In relativity, if you're not accelerating, if you're inertial, you can always say the other person is the one moving and you're at rest. So that means you look at anybody else who's moving relative to you, you say their clock and their time are slow. In special relativity, you'd never look and say someone's clock is running faster than yours. Now, we can look at the implications of this. You can also do this math, if you've got a minute, and plug in the fastest velocity you've ever heard of a human traveling, and you'll see that this factor is ridiculously small. It's very close to 1, and that's the reason it took so long for people to discover relativity.